Hello and welcome to the task Shaded Chopper. In this task, we are finally going to make our own shaders. And the idea is that we have all these different values. We have the light source, we have the viewer, we have the normal, and we also have the position of the thing that we are trying to light or shade. And then we put them all together in these different lighting formulas to create the shading of the surface. And we can see this on the pictures as well. So we have two models that we want to implement in this practice task. And the first one is the go route. You can see that the faces that are more towards light are are lit more intensely, and the faces that are facing away from the light source are in the shadow. The same for the Phong lighting model, but on the Phong lighting model we can also see the specular highlights on the chopper and also on the back wall. And in this practice session, we are going to create the go route lighting model, and the Phong lighting model is for you to implement independently. The only difference between go route and Phong is that the go route lighting model is calculated per vertex, but the Phong lighting model is calculated per fragment. And finally, don't forget to answer this question here: why is go route missing a specular highlight on the back wall? So you can see that Phong has this specular highlight here on the back wall, and the go route does not have it. Now, if you look in the code, we have the main.cpp where we are loading the shaders and creating the scene. So if I activate this program right now, it's just black screen. This is because we still had to implement those shaders. And in the main, we do all the things that we have done in previous task. We are clicking and drawing a hanger. Now we also have create sphere in our implementation. So you can see here that we have this spheroid here, and that's how we make this with this create sphere. And create sphere takes in radius, the width segments, and height segments. And when you add your own chopper to this task, then you could replace the body of the chopper with a sphere, and that will demonstrate much better the lighting model because it has more faces in more different directions. So yeah, you have this task here currently draws a cube and a sphere, but you need to copy your own chopper code here instead. We also have two shaders, and they can be switched between by arrow keys. And yeah, it looks like everything else should be as it is right now. And you can see that when I activate the program, it spits out many warnings. It says that location not found in shader program for variable light position. So this comes from on this line. We are trying to set this light position here, but the problem is that we are not using the light position in our shader, which means that it's optimized out. And since it's optimized out, it does not exist. So it's spitting out warnings. So now let's look into the go route vertex shader. So this is the shader that is run for each vertex that the shader is assigned to. And it has many different uniforms. We have projection matrix, view matrix, model matrix. We also have the light position. So that was the thing that produced warnings. And you can see that it's grayed out. It means that it's not used. As soon as we start using it, the warning will go away. We also have vertex attributes. We have vertex position, we have a color of the vertex, and the vertex normal. And the output of the go route vertex shader is the interpolated color and interpolated normal. That interpolated normal actually is not used in the go route fragment shader, so actually we can delete it. We don't need this. But we will need this in Phong shader, so beware. Yeah, in the fragment shader, you don't need to do anything in fragment shader. We have the uniforms that we are not using. We're just taking the interpolated color from the previous stage and then outputting it as a frag color. So actually we can do it here. Let's define the interpolated color as color. And now if we run it, you can see that the scene is now visible. It was black before because we didn't define this. And you can see the hanger, and we have a sphere and a cube in our scene. So now we just have to start shading these spheres and cubes and walls. But before that, I will briefly show what formula we are going to use for that. So here on the whiteboard, I can show you what formula we are going to use. So we are going to use the Phong lighting model or Lambert lighting model formula. And this formula consists of 3 modules. The first module is for ambient lighting. And ambient lighting is just lighting that comes from around everywhere. And that consists of 2 components. It consists of the material's ambient color and the light color. So if we multiply them together, we get the ambient lighting component. The next component is a diffuse component, and the diffuse component is much more interesting. Well, first of all, it will still have the material color and the light color, but will also depend on the orientation of the face, right? And can illustrate it very well if we have this surface, and let's say that this has a normal as well. And if a light falls from top down, let's say that the light beam is like two dots wide, you can see that the area it lands on is the same as the light beam. But if the light beam is falling on an angle, and it's the same width, so this width and this width are the same, then this is much larger. And this means that the same amount of light is covering more ground, which means that at each point there is less light, which means that it's dimmer there. And how can we do this mathematically? We can use this vector operation called dot product. And what we do is we take the normal vector and the direction towards light, so n and l, and we want this angle alpha to be as small as possible. And if it's smaller, then we want this to be more intense. And that's actually the cosine of the alpha, right? Because cosine alpha, when its alpha is 0, then it's 1. When alpha is 90 degrees, it's 0. So what we want to do is we want to take the dot product of n and l, because dot product of n and l, when n and l are normalized, is just cosine of alpha. So we just multiply this component here with dot product between n and l. And the second, or the third component of the lighting model here is the specular highlights. So you saw before there is this white circle on the chopper and the back wall. So that's the specular highlights, and we have also the specular material color and specular light color. And then we also have something that determines how intense that color is. So to demonstrate it, let's create the surface and let's create an eye. And we also have a surface normal here. So this will also use surface normal. And we will also have a vector towards the viewer. So that would be V. And now we have a light. So let's say that the light comes from here. So this light comes. And now we want to reflect this light. So we will reflect it according to the normal. And this will go in this direction. Let's call it R for reflected light and R1. And now the same thing that we did with diffuse. We want to compare the V and R1. And what's this angle here, beta? The smaller the angle is, the brighter the specular highlight should be. The same way, beta is lower, which means that the highlight should be also lower. So if, for example, we have a light source from here, this will be very similar to V. So R2, not squared, R2. And that angle here is much smaller. So what we want to do is we want this to be influenced with V and R, the dot product between them. But actually that's not enough, because the dot product is a cosine and the cosine is quite smooth. But we want the specular highlight to be sharp, a small dot. So we just take this into the power of shininess, so S, shininess. And that's the lighting model that we are trying to implement today. There are some simplifications that we can do. So for example, we can do that the material of the ambient and diffuse light is the same. So we just move the M forward. And so we can, in the parentheses, do LA. And we can also add then the LDNL. And usually these L's are scalar values, which means that all the channels of the color are the same. So they are like grayscale. So that's also one simplification. And the other simplification we can do is that if you notice, specular highlight is usually always white. So what we can do is we can replace the material and light colors of specular highlight with ones and just add the intensity. So this is the formula that we are going to use today. So back in our code, we should start implementing this formula. So if you remember, we have the position, we have a color, we have a normal. We start using these values to calculate all our different vectors that we need to calculate. So first we need to calculate the vertex position in the camera space. So one thing that I didn't mention before is that all the lighting calculations that we are doing right now, we are doing them in camera space. And we'll see later why this is useful. So what's the vertex position in camera space? We have a position. So that would be the first thing that we use here. So we have the position, but the position is in local space. And to get to the world space, we multiply this with model matrix. And from world space to camera space, we have to multiply this by view matrix. And that's what we have here, this one matrix. So we can just use this. But there's a problem here that this is the 4-dimensional matrix, but the position is 3-dimensional. So we have to convert this into a affine vector. So the last value in the vector has to be 1 here. But there's still a problem that this vector 3 has 3 dimensions. So we just convert this back to a regular vector, not an affine vector. Just take first 3 values of the vector with x, y, z. So now we have the position. To calculate normal in the camera space, we could use this model view matrix. But the problem with model view matrix is that model view matrix has the translation component in it. So it will move things, it will shift things in any direction it can. But if we are shifting normals, then they would not be normal vectors anymore, because they are not 90 degrees from the surface. This translation will break it. It's not a linear operation in 3-dimensional space. So what we had to do is we had to use this normal matrix here. And if you're interested, you can Google this, why we need to do these operations. But this will preserve the 90-degree angle between the surface and the normal. So direction is reserved. So first we take the normal here, which is the vertex attribute, and then we multiply this with normal matrix. But one more thing we have to do here is we have to normalize it. And this is because the multiplication with normal matrix does preserve the direction, but this does not preserve the length of the vector. So we want the n to be with length 1, so we have to normalize it again. Okay, so number 2 is done. Let's go to point 3. Find the direction towards the viewer, and we have to normalize it. So that's the v. And to get to the viewer, we have to subtract 2 positions, right? So let's define a viewer position as well. That would be VP. And since we are doing all the calculations in view space or camera space, by definition, the viewer is in the center of the coordinate system. So it would be 0. It would be 0 vector. And so we have to normalize it. And if we want to go from the position of the vertex, so P, to the viewer position, we just have to subtract them from each other. So VP minus P. And that makes sense because if we add this to P, then the P is cancelled out and we get VP. So that's the vector towards the viewer position. Finally, there is number 4, find the direction towards the light source and normalize it. So that's where we finally use this light position vector uniform. And that would be the L, and we normalize it. And exactly the same operation that we did for the viewer position. First take light position and subtract the P from it. And we can actually go back here and check is the light position also in the camera space. And we can actually see that we define this world space coordinates here for light. And then we multiply this with view, which is the view matrix. You can see here. So indeed, the light position is also in the camera space. So it's very important to check that the vectors that you subtract or add or multiply, they are in the same space. It's very important. One more thing I will define here is the R. So that's the reflected light. And here we have to use this reflect function. And if we look at the definition of the reflect function, we can see that it takes 2 arguments. It takes I and n. So I is the incident vector and n is the normal vector. So n is straightforward, reflect. We have n defined. But what's this incidence vector? Incident vector is just the vector that lands on the surface. So that would be the L, but remember L is towards light, so we want from light, so we take minus L. And the reflect will preserve the length of the vector, which means that if L is with length 1, then the R is also with length 1, so it's also already normalized. And I will also have this S shininess here, and in the command it says like value 200 for initial value. I'll just define it as 200 for now. You can see later what different values look like. So now we can start implementing the formula. So first of all, let's do this ambient and diffuse lighting components. So ambient, diffuse. So remember we had this materials color at the beginning. So that's where we use this color here. So we defined for vertex, the vertex color is this color here. So that would be the material color. And now we are defining the ambient color. So let's define this as, so it has to be vector. Actually, it doesn't have to be vector, but yeah, let's define it as like 0.2. So what's this called? Ambient diffuse. So this not going to be loads, it has to be vec3. So let's see what's the result with just ambient. It's just very dim scene, and it makes sense just we divide this by 5, right? So it's very dim. But now if we add the diffuse component, so let's just say that diffuse strength is 0.8, and if we add them together, then we get 1. So it doesn't get oversaturated. But we now have to add this dot product as well, right? So that would be N and L. And now if we look at the results, you can actually see that there's this light position or light source that's traveling around the scene, and we can see that the light on the sphere changes according to the light position. But one thing you might see, if we make the ambient color more important and diffuse less important, you can see that some places get black, very black, but it shouldn't get black, right? Because the ambient is 0.5. The 0.5 should be the minimum value. It doesn't get lower than that, but it gets around 0 because you can see the black. And that's because the dot product here, the cosine, it also can have negative values. But we don't want this to have negative values. That would mean that if it's lit from behind the surface, it gets darker, and that does not make sense. So what we do is we take the maximum value between 0 and the dot product. And if we look at now, you can see it doesn't get black at all, and it's just like darker red. And if we put them back to 0.2 and 0.8, it looks pretty good. So now we can also see that we can define them as vectors. So for example, if ambient component is 0.0, 0.2, and 0.3, so red, green, blue, so it should be green and blue, so that should be something like this, like cyan, more blue, and you can see that everything has this blue hue. The same thing we can do with the diffuse component. So let's say that this is only red, so 0.3, 0, 0. Really, that's not 0.3, it's like 0.9. So now it looks like this. So with these different modifications to the light color, you can achieve many different results. But for simplicity, I'll just keep it 0.2 and 0.8. Okay, and next we want to define the specular component. So cooler. And yeah, this is also vector tree. And we saw that we simplified the material color and light color to be 1, so white. So let's just first define this component here, the white color. And now we want to determine this, the intensity of the white color. So remember, it was the dot product between the reflected light and the viewer position, or the direction towards the viewer. And we took this to the power of the shininess. So let's just use the function pow and take it to the power of 200. So now we have specular. So if we just look at the specular, you can see somewhere flashes of the specular highlight. Very hard to see them. Oh, there was one. If we make this a bit lower, so maybe 50, you can see they're more apparent, but still very subtle. So if you put it like 3, it like gets gets larger. But now it's not a highlight; it's like a lighting, shading. So the highlight by definition should be like small dot. Yeah, but let's put it back to maybe 15 for now and combine these components together. So we have ambient, we have diffuse, and we have specular. So let's look at the result here. You can see something is wrong. So you can only see the faces that have specular highlight, and everything else is black. And it's the same problem that we had here. So we need to take the maximum value of the dot product, because dot product can be negative. And since it's negative and we take it to the power of 15, gets even larger. So let's just take the maximum value between 0 and the dot product. And now everything looks pretty good. So you can also see that the specular highlight with the white color sometimes appears. And this is related to this question here. Why is Go-Route missing a specular highlight on the back wall? It's the same problem on this surface here. If we have this as a 200, it's very subtle. It's running right now, sorry. So it's very subtle. You might not even notice it with this 200. But when you go to the Phong lighting model, there will be a small dot there. So you can experiment with different shininess values. So yeah, that's the Go-Route lighting model. You have to implement the Phong lighting model. And for that, you need to modify the Phong vertex shader and Phong fragment shader. In the vertex shader, find the correct values for the position and the normal in camera space. So we can see that we have these two outputs here, interpolated normal and interpolated position. So we need to define these in this vertex shader. In the Phong fragment shader, we need to do the same things that we did in Go-Route vertex shader, but there are some small modifications. For example, we are using these input values here, and also this interpolated normal. You might need to do something with this interpolated normal because if you think about it, you have two normals that are facing in two different directions. What happens if you interpolate them? Is this interpolated normal still a normal vector? But I will let you figure this out. And yeah, don't forget to answer this question. Why is Go-Route missing a specular highlight on the back wall? If you have done the Phong lighting model and answered this question, then you have finished this task.